Going over number 12, I'm going to do D and F from the 2013 exam 3. Right. So D is this plus, it says BH3 is step 1, step 2 is OH minus H2O2. Right, so I'm not going to go through the mechanism here. We've done the mechanism a couple times already. Hopefully you have your notes. We've done it in class multiple times. But the key here is, right, first step, let's number our carbons. 1, 2, 3, 4, 5, 6, 7. So we numbered our carbons. You see BH3, and you realize what are you going to add? What kind of functional group are we going to add? An OH, right? We're making an alcohol. And what carbon are we going to add it onto? 2 or 3? Nope. We're going to add it on to 3, right? BH3, remember, is the one example we have that gives us the anti-Markovnikov product. But are we done if I put it on? So I put it on carbon 3. So let's number again. 1, 2, 3, 4, 5, 6, 7. All right? But I need to add more here, don't I? What else do I need to add? I need to add the hydrogen. Sure. It's on carbon 2. And there's an H here. What else do I need to include? Stereochemistry. What kind of addition does BH3 do? Cis addition, right? So it gives you the anti-Markovnikov product. The OH ends up on the less substituted carbon, right? And it's a cis addition, right? All at once. So here you could draw it two ways. Draw both enantiomers. The H would be hatched. So the H and the OH have to be on the same side, right? Plus, you would have the other enantiomer, where the H and the OH are up, and the methyl and this H are going back. Right? So you'd have both enantiomers in this case, this product. Okay, we're going to do F first. Right? You got to do F first. All right, let's do F first. So F involves H plus as a catalyst, and then methanol as a solvent. All right. Number our carbons. 1, 2, 3, 4, 5, 6, 7. First step, what's my electrophile, what's my nucleophile? Pi bond's the nucleophile, H plus is the electrophile. So what are we going to form here? Where should I put the plus charge? It really doesn't matter here, right? So you can put it on 4 or 3, right? 4 would lead to a secondary carbocation. 3 would lead to a secondary carbocation. But let's just say I put it on 3. I put the plus charge here. Oops, that's 7, 6, 5, 4, and 3. There's a secondary carbocation. Can I make it more stable? Yep. Right? Anytime you form a carbocation, they'll rearrange, right? So you should have saw H plus and ethanol, or HBr, HCl. You should think carbocations, they'll rearrange. Right? This case, we'll move the H that's on carbon 2. We'll do the hydride shift, and you've got to show those arrows doing this. You've got to show those arrows. Now, where's the plus charge? Carbon 2, good. Now let's have our solvent come into effect. Or you know we're not done, right? Because also another thing we should have saw, the H plus is a catalyst. So we know we're not done unless we've regenerated H plus, right? We've balanced our charge, good. What's my nucleophile, what's my electrophile in this step? What's my nucleophile?
The lone pairs in the
Lone pairs in the oxygen, the electrophile is? carbocation, carbon 2. Right, so you start your arrows always at electron density. Number our carbons. Did I balance my charge?
No.
Where's there need to be a plus charge? On the oxygen. Does everybody see that? This is a point of confusion people always make where they want to break this bond, they want to break this bond right away. Nope, the lone pair is the nucleophile. So the lone pair attacks. The H and the carbon are still bonded to the oxygen the whole time. Alright, so we still have the plus charge on the oxygen. So how are we we need to regenerate the H plus. So the last step we do is the electrons between that OH bond go to the oxygen. And we've remade H plus, and we have now the O, right, we've made an ether, and we also have H plus around as well. So 1, 2, 3, 4, 5, 6, 7. Make sense? Yep, good point. The stereochemistry for this, at carbon 2, you'd have, right, since you have to go through a carbocation, we know carbocations are flat, so you could attack from the top or the bottom. So you'd have, right, in one case you'd have the O wedged, the other case you'd have it hatched. Right, so you'd have both, and you'd have both products there. But is that a stereocenter? Is carbon 2 an asymmetric center?
No.
No. So it really doesn't matter, right? Carbon 2 is not asymmetric, right? Because if you go this way, it's not different. It's the same. Remember, asymmetric centers, sp3 hybridized, 4 different things. So 12B again on the 2013 exam. Got the ozone. How to look at this, basically, I mean, number of carbons, 2, 3, 4, 5, 6, 7, 8. We cut the double bond down the middle, right? And what was an alkene now becomes 2 carbonyl groups. All right, number of carbons, 1, 2, 3, 4, 5, 6, 7, 8. Just split it right down the middle. So again, number 12A and 13, or 2013 exam 3. Quiet down. So let's do the mechanism for this. So it's actually very similar to the one we just did, but with a little added wrinkle here. Again, H plus is a catalyst. Now it has water as a solvent. Number of carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. First question we ask ourselves, what's my electrophile, what's my nucleophile? What's my electrophile? H plus is my electrophile. Nucleophile is the pi bond that attacks. We're going to form a carbocation. If we form carbocations, we know we could rearrange, right? So we got to be leery of that.
Could it go on 3 or 4?
It could again go on 3 or 4. That's right. Right. So not a very good question. I don't know who wrote this test. Right? It could go on 3 or 4. Right? Ideally, you went on 3, then you had to do some other stuff. But if you went on 4, we were kind of stuck, and we had to just give you the points. I will not let that happen again. Right? So you have carbocation there. A little different wrinkle is there that carbon 2 and carbon 7 are both asymmetric centers, right? So what's going to happen, though, again, right, we have a secondary carbocation. Can I make it more stable? How can I make it more stable? Make it a tertiary. How do I make it a tertiary in this case? Shift the hydrogen from which carbon? Carbon 2. So that shifts over. Is there still a wedge and hatch bond on carbon 2?
Yes.
Where's the carbocation at? Where's the plus charge at? So if you're carbon 2, if you're a carbocation, are you wedged and hashed anymore? No, you're flat because you're what hybridization state?
SB2.
sp2. See? There it is. So you just killed that stereo center.
Why is it SP2?
It's carbocation. Carbocations are more stable as sp2 hybridized, right? Electrons get away from each other. Right? So now you have a tertiary carbocation. The trick here is, can you keep rearranging it?
Yes.
Should you keep rearranging it? No, right? Because carbocations only go downhill. If I have a tertiary carbocation, if I can form another tertiary carbocation, will I? No, that's a sideways move, right? So even though, right, there's an H at carbon 7 that could shift, that would still give me another tertiary carbocation. There's no reason for me to move sideways. So I'm not going to do it. All right, so that was kind of the trick here, was to kind of not do a rearrangement. If you already have a tertiary carbocation, you won't make another tertiary one. Just like if you have a secondary, you won't turn into another secondary, unless there's extenuating circumstances like ring strain, which we all saw. So again, what happens? It attacks.
Ours is H2O.
Oh, just made that up. Who can keep track of these things? All right, there's a learning experience. Good job. You caught it. I want to draw it again. There it is. All right, a lot of water around. That's going to attack. Again, notice, right, when it attacks that carbocation, does it have a preference for the top of the ring or the bottom of the ring? No, because carbocations are sp2 hybridized and flat. Right? So you're going to form, at that asymmetric center at carbon 2, you're going to form both wedged and hatched. But now be careful. Let's draw both the wedge and hatch. Let's draw first out what happens. Because we're not done with the mechanism until we've regenerated our catalyst too, right? 1, 2, 3, 4, 6, 7, 8, and 9, right? So I need to regenerate my catalyst, so have the electrons from the O go to the oxygen. Right? So I'm going to have both the wedge OH, right? If I number my carbons, 1, 2, 3, 4, 6, 7, 8, 9. I'll have this version. Will I have the other version too? Where the OH is on carbon 2 is going wedged? Yes, I will, right? But the neat part about this one, neat to me, is we didn't make enantiomers here, did we? What did we just make? We made diastereomers. Right? Notice carbon 7, that stereo center, that asymmetric center, never changed throughout the whole thing. It just stayed the same. Right? So in the end products, that stereo center is the same. So they have one stereo center is the same. And their other asymmetric center is different. That's the definition of a diastereomer. Right? At least one asymmetric center the same, and at least one different. So now we made a pair of diastereomers. In diastereomers, you can separate. Do diastereomers have different physical properties? Yes, they do. Right? Unlike enantiomers, which have the same. So sometimes it's nice to make diastereomers. They're easier to separate.
Did that hydrogen go to, where did that hydrogen go?
This hydrogen, yep, good. Whoop, didn't balance my charge. I had to make, right? I also made H plus at the end, right? So I had to regenerate my catalyst, right? That's what, right? This little arrow right here is showing, right? The electrons from that OH bond going to that oxygen, right? I had to regenerate my catalyst. Good. Number your carbons. What's the electrophile? What's the nucleophile? Am I blanking? Balance your charges. What's the last one? Number your carbons.
Either way.
Identify the electrophiles and nucleophiles.
Regenerate your catalyst.
Balance your charge.
Are we gonna be asked to do like on-program?
You could be asked to do that. So the things you've been asked to do. Number your carbons is first and foremost. Number your carbons. At least let me give you the benefit of the doubt. Bonds broken, bonds formed. If you can, if you have the product, you should be able to do bonds broken, bonds formed.
Like name them?
What?
Name them?
Like, yep. No, I'm just naming out how to go through these problems, right? Yep. So yeah, you want to name out which bonds were formed, which bonds are broken. But you only can do that if I give you the start material on the products, right? Balance your charges. Identify your electrophile and nucleophile for each step. Always balance your charges. Make sure you do that. So, good question. So, just for ease of use, I didn't, right, there are wedges and hatches here. I just didn't put them in here because I didn't want to draw it twice. Right, I would have two of these formed. One with the OH wedge and one with the hatch. I just didn't draw it twice. So this is a naming one from the 2013 exam. It is, let's see. It's 2000, it's number 6, 2013. So naming problems, you got to find the longest, this is find the parent chain with the longest, the parent chain with both of the functional groups in it. Right, so both functional groups are the alkene. So it's just, I like to circle that. Has to be the longest continuous chain. So we know off the bat how many carbons is this? It's 1, 2, 3, 4, 5, 6. So you know we're going to have a hex something, hexadiene. Right, so we're going to have a hexadiene. Right, we're going to have a hexadiene. We need to say which numbers though, right? We need to say where that diene's at. Right? Right, so where do we want to put that number? So we can number it one of two ways, right? We can either number it from this way, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. How are we going to decide?
The first way,
The first way, why?
because it gives the substituent the lowest.
Right? In this case, right, we usually want the alkene to be the lowest as possible, but here 2 is 2, right? So if we can put this 1, 2, 3, 4, this butyl group, have a lower number, we will. So we'll number it this way. 1, 2, 3, 4, 5, 6. So the double bond is at 2, 4 hexadiene. And at carbon 3, there's a butyl. So 3 butyl, 2, 4 hexadiene. This is how I would have named it.
You have to do the.
This is fine. Yep, so we're not done. We're not done yet. Right? Because we still have to worry about E and Z, right? So first we got to make sure our alkenes can be E or Z. We both know that at carbons 2 and 4. So at carbon 2 and 3, if we split that in half, right? What kind of alkene is that? What kind of alkene is that? E or Z?
E.
It's E. So we'd say we put this out front. 2E. And what about the one between 5 and 4? What kind of alkene is that? Also E. So we'd say 4E. Yep. So you draw your H in. Right, carbon 2, who gets the highest priority? This carbon does ahead of H. Now we're looking at this, carbon to carbon, tied. Carbon to carbon, carbon to carbon, still tied. Carbon to carbon, carbon to H. Winner. Right, so they're on opposite sides, so that's E. Right, so it's just like assigning priorities like R and S, right? This way has a higher priority than this way. Right, this carbon, right, is bonded to a carbon. This carbon is bonded to a carbon, tied. 4 bonded to another carbon. This carbon not bonded to another carbon, bonded to an H. This one wins. Right? This one's a little easier, I think, to see. This is H's. So. All right, number 27 from chapter 6. Right? This has to do with an alkene and Br2. Number of carbons. 1, 2, 3, 4, 5, 6. I'm not going to do the mechanism. We've belabored that. We've done the mechanism before. You can only do it so many times. You should start seeing that. Right? What do the intermediates look like, though? How do we draw the intermediates?
Yeah, but how does H2 go in there?
It doesn't matter. Well, it's going to matter eventually, but it doesn't matter for the intermediates. Right? So all you need to do is see the intermediates. Let's see if you can see the intermediates. So we all know carbon 1 and H are on the same side of this alkene, right? Carbon 5 and carbon 4 are also on the same side of the alkene. So when we draw this, right, the Br, the bromonium ion, can either be on the top or it could also be on the bottom, right? The way I like to draw them, it's not, you don't have to do it this way. I think it's just easier to see. I will just draw it out initially like this. Right, and I will arbitrarily choose carbon 1 and H to be wedged. Arbitrarily choosing that. I just know if 1 is wedged, then H better be wedged too. Right? So let's just say that's 1. That means that's 2, 3. And then this right here is going to be H. Carbon 4. Right, if you look at carbon 4 and 5, again, 4 and 5 are on the same side. They're both going to be wedged or hashed this time. And I just randomly chose this. Right? You could have easily done these wedged and these hatched. You've got to be consistent the whole way through. Right? So this is carbon. I need to draw carbon 5 is out here. It's also bonded to 6. And this carbon over here would be carbon 4. Right? And the first way I'm going to draw it, the bromonium ion with the plus charge here. So that's one way the Br could sit, right? Br could sit on one side of the alkene, that way. It also could be like this. Notice I'm not going to change anything about the wedges and the hatches. Nothing. Nothing's changing. I'm just going to continue to draw the way I drew it the first time over and over again in the starting materials, in the intermediates, and in the products. Over and over again. Numbering carbons helps to keep track of things. But now instead of the Br being on the top, the Br is going to be on the bottom. Right? Nothing else has changed. But the Br is on a different side. Right? So at this point, if water's in there, you should know about bromonium ions that they end up with what kind of products? Trans products. That means the nucleophile that attacks has to attack from the opposite side. Right? So if the Br plus is up on this side, where's the nucleophile going to attack? From this side. Now also, what carbon is it going to attack? Carbon 2 or carbon 3? It's going to attack carbon 2. Carbon 2 is more substituted. It's more likely to be delta plus because it's more substituted. Right? So have it attack carbon 2. As that bond breaks, the carbon-bromine bond breaks. Same deal with the other way, except it's coming from the other side now, right? So it's always going to be trans. But that would give you two different enantiomers, right? So the final product, or at least if I just draw one, if I said this was A, and this is intermediate B, let me just finish with A, right? Again, notice, not changing, just keeping this the same. The Br is up. The water, which is added, has a plus charge. There's still Br minus around because we need to balance our charges, right? Should have been Br minus over here too. Balance our charges. That's a rule. So the final step is making HBr. And that gets you to the product. You'd also have the enantiomer of this as well, right? Which comes from intermediate B. So this is the way I like to draw it. I like to draw it like this because you don't need to worry about the wedges and hatches. It just stays the same all the way through. I think it's a lot harder to mess this up. But if you want to do it the different way, by all means. If it's easier to see, it's totally cool. This is the way I see it. So I'm going to do a free energy diagram for this. I'll do I'm going to call this A1. I'm going to call this A2. And then the final product will look like this. Keeping this the same. Over and over again. Just the same. One, 5, 6, 2, 3, 4. BR up, OH down, and I had HBr. And this will be A prod. Alright, so how many intermediates did I have in this reaction? If I'm just looking at A, how many intermediates did I have? I had 2 intermediates. How many arrows were there? There should be an arrow here. How many arrows were there? 3 arrows. 1, 2, 3. So how many hills do I have? 3. So every arrow is a hill. Every intermediate's a valley. So starting materials there. Which intermediate is the highest energy, do you think? A1 or A2? A1 why? No carbocation. Bromonium ion, right? So you have a plus charge on the bromine, and you have the bromine in a 3-membered ring. That's not happy, right? So let's just say A1's up here. What about A2? Is A2 going to be higher, lower, the same as A1? Should be lower. I don't know where exactly. You just need to know, relatively speaking, it's lower. So this took a lot of energy. This probably didn't. And then this certainly did not go to products. Does the free energy diagram for the B pathway look any different? No. Because they're enantiomers. And do enantiomers have the same physical properties? Yes, they do.